Good morning, good afternoon, good evening, wherever you are on this planet, and welcome to our SETI Live. My name is Frank Marchis. I'm a researcher at the SETI Institute, and today we are going to talk a very special planet called TOI-2180b, a gas giant which was found by citizen astronomers and studied a posteriori by professional astronomers. So to talk about this, I invited two people involved in this research. So first of all, far away from me, we have Daryl Lacours. Hi, Daryl, how are you?
Hey, thank you for having me.
So Daryl, you are where you are calling us from?
I'm up in Seattle, Washington right now.
Okay, so we are going to talk about your contribution in this remarkable discovery. And on my right here in my shed, nobody ever come in my shed to do a SETI Live. So you're the first one. Yeah. Paul Dalba. Paul Dalba is the lead author of the paper that was published in January 13.
Yes.
On the discovery and the characterization of this interesting exoplanet. So before we talk about this in more details, I would like to mention to you that feel free to tell us on the chat where you are watching us from, so we have an idea of our outreach, because this is an outreach program. And yeah, let's talk about the discovery. So Daryl, you are not a professional astronomer. You are what we call a citizen astronomer or amateur astronomers. How do you prefer to be called?
Amateur astronomer, citizen scientist.
Okay.
Yes.
So tell us a bit about how this group and has been basically contributed to this interesting discovery.
Yeah, sure. So there's 7 of us on this group. We have this moniker, the Visual Survey Group, but we all started looking at Kepler data as volunteers on the Zooniverse project, planethunters.org, which crowdsourced Kepler data starting in about 2011. And several 100,000 people participated in that. And that project, to make a long story short, proved very good at picking up planet transits that the computers missed back in the early days.
Mm-hmm.
When that mission wrapped up, the K2 mission kind of picked up where it left off in a very similar manner with shorter baseline looks at different chunks of the sky. And when we ran out of data with K2, there was kind of some downtime, and a few of us hadn't quite had enough, and we had all met on the web forums at Zooniverse and whatnot. And so we kind of waited patiently for TESS to launch and get deployed. And of course, the data is open to everybody to sift through as soon as it downloads off the spacecraft. And so Tom Jacobs, one of the members, and also the gentleman who first detected this planet we're going to talk about today, took the impetus to kind of round us back up and put the band back together, so to speak, so that we could continue to do this sort of work with TESS data, effectively to continue probing long period planets. Kepler found long period planets, but didn't quite probe into that area of parameter space quite the way that maybe everybody had hoped, citizens and professionals alike. So we had the idea that as soon as the data comes down to Earth, we can probably find good transits a little quicker than the pipelines can sift, sort, and validate them, because computers are still not superb at detecting single transits on their own and deciding that's a good planet, right? Whereas human pattern recognition, I think, proved in the Planet Hunters projects and the derivatives of those crowdsourcing projects that people are actually very good at telling a transit from a false positive drop in the light, or many of the other things that can kind of trick the computers. So the advantage of the way we look at the data is that we can sometimes pick good nuggets out of the haystack pretty quickly and give professionals like Paul maybe a bit of a head start to go get after these and start an RV campaign or other sorts of ground-based follow-up to turn them from a candidate into a confirmed exoplanet, like what has happened with this object.
All right. Yeah. So tell us a bit about this subject, the discovery of this object. Can I show the light curve?
Yes.
Yeah. All right. So this is a light curve. So just maybe Paul, you can explain while I'm trying to find how to share my screen. You can explain what exactly is this light curve.
Sure. Okay, there it is. So the general idea of a light curve and what we're trying to do with the TESS data is just measure how bright the star is as a function of time. So that's what we see on the y-axis, brightness, and the x-axis is time. So as we go along in time, we see the star is relatively steady brightness, and then all of a sudden, boom, there's this big drop off. And it kind of has this characteristic U-shaped pattern that is very characteristic of an exoplanet crossing in front of the face of a star. So that's what we look for. That's what the visual survey group tries to find.
So, Daryl, when you who made the first discovery of this? You get the data from the spacecraft, you display them. So how do you organize your group? Who's basically how you split the work between all of you?
Well, we actually don't split the work. We kind of go on a many eyes make quick work sort of principle. And so in this case, well, every sector that comes down, we all independently survey it and then collaborate on our results. And Tom happened to be the first one to come across this light curve in a piece of custom software we use to allow us to kind of very quickly go through the data for a quick look. And this is really a beautiful textbook transit right here. And so Tom immediately emailed our citizen science group. And the way we kind of collaborate is to just compare notes and say, hey, do you think this one looks good? Should we forward it? Should we list it? Should we put it on the back burner for later? And we all immediately agreed that is definitely a good transit candidate. It doesn't get much better than that, honestly. So in the TESS mission, one of the roles I've played is to help coordinate in between Paul's group. The working group we're a part of is specifically looking for these objects that just transit once in an individual sector of TESS data. Hard for computers to find, but when they're this good, easy for humans to pick out. And so in that way, we were able to kind of get a jump start on some monitoring for this object. So basically, as soon as we had all seen it and all 7 of us agreed it was good, we forwarded on to our professional collaborators. And then they really started the hard work, which is getting the telescope time and everything that's detailed in the paper that eventually turned this from a candidate into a confirmed exoplanet that you can bet the bank this is the real deal.
All right, let's talk about that, the characterization, because I think that's where your team's been involved, right?
Yes, that's right. So that's where I came in. So I received the email from the visual survey group, Daryl and co. I think the words in the email were too good to be true, but indeed it was true. I also jumped when I saw the transit. So I have a program I maintain on the Automated Planet Finder Telescope, which is a telescope that exists at Lick Observatory, which is in the San Jose area of California. And it's a robotic telescope. So I can just upload a star that I want it to observe and how often I want it to be observed and all the requirements. And then I can get data in the morning after it happens. And so that is the main facility that we used to characterize this system. So the particular technique that we used was the radial velocity technique. And this is whereby we look at the star itself. We're not actually looking at the planet. We're looking at the star and we're looking for the gravitational tug induced on the star by the planet. So the star actually wobbles back and forth as the planet orbits it. And that is the wobble that we're highlighting here in these radial velocity data. We call it radial velocity because we're looking at the velocity on the radial direction to the star.
So we don't see the planet either here. We see the effect of the planet on the motion of the star.
That is correct. Yeah. So we watch that wobble. And in this case, you can see there are 2 very clear wobbles that occur over about 500 days. And that gives us 2 really important pieces of information. One, it tells us the mass of the planet, how much material this planet has. And that lets us know that indeed it actually is a planet as opposed to something much, much more massive like a star. And the second piece of information is it tells us the length of the orbit that planet has around the star, the duration of its year, which in this case turned out to be about 261 days or so.
Okay, so this is a planet which orbit around the star in 260 days. Most planets we discover and people have heard about, they orbit around the star very quickly, right?
Yes, yeah, especially those that transit their host stars. Yeah.
So that's why it's a kind of a special case. It's a rare exoplanet.
Yeah, it kind of hits this kind of trifecta, as I've been calling it, of rare properties. One, in that it's relatively close. The star is relatively close to the Earth. It's about 381 light years away. And then the second part of this trifecta is that It has this 261-day orbit, which is fairly far away for that planet to be orbiting from its star. And then the third part is that it actually transits. So it's very rare for a planet to have all three of those things: the system to be close to the Earth, long period orbit, and to transit the star. So the fact that it does all three makes it the very rare planetary system that it is.
Okay, so to summarize, we let me just see how people are calling us from, and then we go back to the science. So we have people watching us from Ohio, Alaska, Birmingham, UK, Alberta, Canada. Thank you, Paula, for the stars. Knoxville, Virginia, Guelph, Canada, Arkansas, Los Angeles, Missouri, San Francisco Bay Area. That's probably the people at the SETI Institute. Spain, Glasgow, UK, in Louisiana on the Bayou. And thank you, Ron, for the stars, Maryland, Georgia, etc. So we are talking about the discovery of a gas giant exoplanet, a long period exoplanet, which was made thanks to the contribution first of citizen astronomers and then professional astronomers. So we talk about the fact that you, Darrell, the visual group, discovered the transit. You characterize the planet by radial velocity. So now you know it's a gas giant because you have the mass and the size, so you have the density, right?
Yes, we do.
Which is roughly the density of what, Jupiter?
It's a little bit more massive, so it's a little bit more dense than Jupiter.
Okay.
Yeah.
So we know there is something slightly more dense than Jupiter orbiting around this star, 380 light years away from us, and in 300 days or something like this. So what else? What happened now?
So as we were watching the wobble of that star, we saw the star wobble about one full time. So we knew the planet must be close to transiting again. And we really want to detect a second transit, because if we can do that, then we know the length of this planet's year really, really precisely. And that allows us to predict future transits that we might want to observe with other telescopes or space telescopes, things like the James Webb Telescope. But we have to detect that second transit. We have to catch it. And so that's when we kicked off a large worldwide campaign to keep eyes on this star. So based on that wobble data, we had about an 11-day window where we thought the transit might occur. And so we needed to observe this star for 11 days straight. And that's impossible to do from any given location because the sun rises every day. So we stitched together about 14 different sites around the world over 3 continents in the Northern Hemisphere. And that produced dozens of data sets and tens of thousands of images of this star over the course of those 11 days.
So for 11 days, people around Earth used their telescope to observe this star in the hope of detecting this transit.
That's right. It was amateur astronomers, citizen scientists, professional astronomers. It was a huge collaborative effort.
Darrell, do you have a telescope yourself?
I live in Seattle, so no. What would be the
That's true. Okay, well, we will let you use some of our telescope remotely. That will be a solution to your problem. Okay, so what happened?
Yeah, so we did this campaign. I did observing myself out in Joshua Tree National Park.
Oh, you went there by yourself?
Yes, yeah, I took 2 EV scopes and went out there and did that. And so at the end of this whole campaign, alas, we didn't have a home run fireworks detection of the transit. But what we did have was many strong non-detections. We had many times when we could say, we are certain that we didn't see the beginning or the end of a transit at this time. And that allowed us to refine what we know about this planet's orbit a little bit, enough to make a prediction for the following transit after that one.
All right.
So it was still successful.
Still successful and still enough to publish a paper.
Yes.
All right. I just would like to mention to our viewers, they can ask questions. We're going to take a few questions since we have some time, but I would like to clarify a few things before we go to the questions here. So we failed to detect this transit, right? But you have an orbit.
Yes.
Okay. So when this planet is going to transit again?
Well, that's the exciting thing. Based on the information that we have, we were able to predict 2 new transit windows. And one of them was just several days ago on about January 30th, give or take a day. And the next one is in a couple days from now, February 5th, give or take a day. So a transit is going to occur in one of those 2 windows. That's our prediction.
So now if you look in the sky and you look carefully at TOI, I forgot the number already.
2180.
2180. And you have these bionic eyes, which allow you to measure carefully the photometry, the brightness of the star. You may see it dim due to the fact that there is a planet like Jupiter passing in front of it.
Yes, yeah, it's a very small dip. It's about less than 0.5% decrease in brightness when this transit occurs.
So that's the reason we need TESS to see those things, because TESS has a capability in space to see that.
Yes.
A lot of data come from TESS because TESS has a wide field of view. So thanks to you, Darrell, and your team, we have people looking at this data to alert quickly when there is something happening, so you can do the follow-up. So is there anybody observing this star at the moment?
There are a handful of citizen astronomers. I know, a small group, not quite as large as the last campaign. But in addition to that, thankfully, TESS is also looking in the right part of the sky to be observing this star right now. So the hope is that TESS will catch this new transit itself.
Oh, nice. So we will have probably another detection from the TESS spacecraft.
Yep, and I bet that detection will come from the visual survey group.
All right, so you ready, Darrell? Are you looking at the data already, or?
We are.
And?
On it.
Okay.
It'll be a while till it comes down.
Okay.
An interesting thing about TESS is that there'll be many opportunities like this from TESS candidates that we didn't have with Kepler, because a lot of the Kepler targets were much dimmer, and TESS is a mission that's a little more focused on these nearby bright stars. So like Paul said, there's a kind of a trifecta and many interesting, unique sort of things about this candidate, but there's thousands of TESS candidates already, whether they're pipeline detected or detected by citizen scientists on the Planet Hunters TESS project or by my group. So I think in the future, there's many more opportunities for people to get in their backyard and try and do this sort of campaign that Paul has been describing.
Excellent. So before I go to the questions, we have people joining us from Montreal, Quebec, Scotland, Wisconsin, Trinidad and Tobago, Prince Edward Island. That's something I need to know, where is this island, and more. What's the magnitude of this star?
It's about 9th magnitude.
9th magnitude, yeah. So with this telescope here, we can observe it without any problem. So a small telescope can help characterizing the depth of the profile of the transit if you have the photometry that you need. All right. So I have some very unpleasant questions to ask you too. So you have been working on this planet, and I'm very disappointed to see that he has no name. And I know a lot of people are complaining about that. So could you explain to me why? What is this TOI? Why do we keep this TOI name?
Sure. So TOI is an acronym, stands for TESS Object of Interest. So when we first identify this as something that might be a planet candidate, as Darrell explained earlier, it's identified with this TOI number. It gets a unique number that's assigned to it. In this case, it was 2180. In previous missions, like the Kepler mission, once it was determined to be a planet, it would then be elevated to have a different name. Like the KOI, Kepler Object of Interest, would then turn into a Kepler planet. We do not do the same thing with TESS. It just maintains the TESS Object of Interest number. It's one less set of numbers to have to remember. Otherwise, you have two numbers that are both associated with the same object. Beyond that, I think it's just organization standards. I did not make this choice, but
you need to change this.
I need to make an argument.
What do you think about this, Darrell? You like those numbers?
I do find it a little simpler. It would be nice if every single confirmed exoplanet could have a nifty, unique name. But who's to really decide that, right? I think the main point of the work right now is to explore and see what's in the local neighborhood. There'll be plenty of time down the road to kind of give better identifiers to the best of the planet candidates that we're the most interested in knowing more about, including perhaps this one someday.
Yeah, last weekend they announced that TESS discovered 5,000 target of interest already.
Yeah, that's right.
Incredible. So there's a lot of work for you, Darrell. I'm sure there is a lot of others planets in this data set. But I'm sure you haven't. You don't give a nickname to those planets. You don't try to kind of make it easy, or even call it the Darrell planet or Tom planets, or what? You don't have some kind of nickname.
Honestly, no, we have not yet reached that pretentious level where we're naming planets after our children or my dog Jack here or anything like that. It's not a bad idea. Maybe I'll float that. Maybe we pitch it to the IAU.
for the next one.
Yeah.
Okay. We have a questions about, are there coordinates where people should look? Yes, any stars in the sky has what we call a coordinate, a radix. And it's somewhere in the paper, and I'm not going to quiz you on that, but where it is.
Let's see. I believe it's the right ascension is 18 hours, and I think the declination is on the order of 45 or 48 north. So you have to be in the northern hemisphere to see it.
Exactly, and you can see it now. In fact, so.
It is, yes, visible now.
All right. More questions. So, what do you expect from JWST with this planet? Any project with that?
Yeah, so it's an exciting prospect. So with James Webb, what we can do is look at this planet in more depth and perhaps try to characterize more about the system or even the atmosphere of the planet. So we want to try to see what reflected light might look like coming from this planet, or what light emitted from the planet itself might look like, and what that might tell us about clouds in the atmosphere of this planet, or what might be going on right at the deepest level of the atmosphere that we're able to see. I also think that would be very exciting, and this is a little more speculative, but what's really exciting is the possibility of this planet having a system of rings or a system of moons, exomoons. So far, there has been no strong, confident detection of a moon system or a ring system for an exoplanet. But just borrowing from solar system intuition, this is a large gas giant planet. Just think of something like Jupiter or Saturn. Saturn has many rings and many moons, and Jupiter has large system of moons. So it'll take the power of something like JWST to try to search for those types of interesting properties.
So is the star the planet located in the habitable zone of the star?
It's a little bit closer in. So the temperature, I think, is on the order of 170 something degrees Fahrenheit. So it would be a bit warm. It's not quite habitable.
Okay, so it's like Venus.
It's a little bit more like Venus, yeah.
So the star is a G5 star, right?
Yeah.
Mm-hmm. Yeah, so it's a solar size. Okay, good. Do you see any more planets, or do you expect to see more planets in the system in the future by observing it transit again and over?
So we don't have really any evidence to suggest there are other planets, or I'd say smaller planets within the orbit of TOI-2180b. However, in that radial velocity, that wobble data, on top of the back and forth wobble of the star that we saw because of the planet that we discovered, there was a one direction drift. So the whole star was drifting in a single direction, and we didn't resolve the entire orbit causing that. So there is something else in this system. I don't know if it's another giant planet. I don't know if it's perhaps a small star, a very small, cool star that's also in the system. It's going to be much further out than TOI-2180b, and we just have to continue our monitoring with the APF in order to determine what else that object could be.
All right. We have people joining us from Cape Elizabeth in Maine, Paracao in New Zealand, Tokyo. Thank you, Patrick, for the stars. Yeah, I have a question for you, Darrell. People want to know how they can join the group, or if there is another way they could contribute to the same type of research.
Yeah, absolutely. One thing that's very interesting about this sort of astronomy is it may be very complex, obviously, in the follow-up, but anybody can very quickly get involved in this and have success at identifying a real deal transit. If anybody's interested, my advice would be to go look at the Planet Hunters TESS project, which is basically an extension of the same sort of project we ran for Kepler and K2. Anybody can sign up, and through your web browser, you can immediately begin randomly sorting through this data as it's downloaded from the spacecraft. Not in real time, but they are pretty good at very quickly ingesting new data and making it available to the public. And as you can see with this clear transit, it's got a good signature, and anybody really without having a big technical background or math background or even an astronomy background at all can get involved in this and have a lot of fun going through the data, quickly identifying planets that the Planet Hunters TESS project has a series of papers. I think actually, Paul, they independently discovered this object as well through the crowdsourcing. So there's certainly many avenues to get involved through crowdsourcing projects. What we actually use to look at the data, incidentally, is a piece of software that was freely developed by a wonderful man named Al Schmidt, originally in Kepler, to look for exomoons. He built it originally to quickly look at beautiful, clear transits like this and look for those signatures of moons. And anybody's free to go find the LC Tools website and request a copy. And so they can also look at the data in that manner, the same way that we do. There's just some subtle differences in the interface, but effectively you're looking at the same light curves in the same manner of detrending. So planethunters.org would be where I would start if you've never heard of this and perhaps are interested in doing a little exploring of the neighborhood locally here.
So Darrell, do you co-author of this paper with the 7 of you are co-author on this paper? Or is that your first scientific paper?
No, we've been really blessed to be involved in a lot of collaborations, starting back in the original Kepler Planet Hunters project. I don't know. I don't know how many papers
Okay.
have been involved.
But you co-author.
You know,
That's important. I just want to mention the fact that, I mean, the community of asteroids has been working with amateur astronomers in the past, and often they're not co-author of the paper. So I'm glad that to see them in this one.
Absolutely.
I will say that is something that I love about this community and this science is through the whole 10 years I've been involved in this little hobby, this is a very open and inclusive community. I can't say enough about the professionals like Paul, who are always happy to have the help. We really get to do the fun stuff, right? We don't have to teach. We don't have to seek tenure, worry about finding a new job if you're a postdoc.
Yeah.
And obviously I can't speak to other fields of science, but I suspect that this particular area is one of the most inclusive as far as collaborating with amateurs. So nobody should be shy about getting involved in this if they don't have a technical background or an astronomy degree or anything like that. The more the merrier.
Absolutely.
Yeah, with so many exoplanets discovered, I mean, so much data coming from TESS and other missions in the future, everybody will be able to contribute and maybe find their own exoplanet. And that's a kind of a nice field to be, a nice moment to be working in astronomy as a professional or as a citizen astronomer. But thank you very much. Thank you, Paul.
Thank you. Yeah.
Thank you, Darrell.
Thank you.
I hope to see you at SETI Institute soon. We have a new headquarters.
I would love to get somewhere warm again soon. So
okay. Yeah, it's 18 degrees Celsius right now here. Okay, well, thanks a lot to you too, of course, to all our viewers on YouTube, Facebook, and Twitch, and so on. Thank you for supporting us. We are the SETI Institute, a non-profit organization. We are searching for life in our galaxy, any type of life, microbiological life to intelligent life, intelligent signals as well. If you want to support us, you can do it by simply following us on social media, sharing this video, commenting below, so more people can see this video randomly on YouTube. And also, if you feel inclined, you can also make a donation. You just go to seti.org/donate and make any donation you want, $1, $1 million. We can buy more coffee for Paul to find more exoplanets, or fly Darrell to the SETI Institute so he gets finally the chance to get a warm weather for the winter. Okay, thanks a lot again. And I would like to mention that next week we have a SETI talk on the very interesting topic that I've been looking forward to discuss with all of you, whales and their intelligence. We are going to talk about this intelligent species in the ocean, and how we try to understand how they communicate, or maybe if they have a complex language. So this is gonna be on February 15 at 11 a.m. Pacific time. This time, if you want to see this talk live, you will have to register. We are not going to stream it on YouTube or Facebook. You have to go to our registration page and you will get a link to follow it on Zoom. So thanks a lot, everybody. Bye-bye. Bye, Paul.
Goodbye.
Bye, Darrell. See you
Take care,
soon.
all.
See you for another exoplanet in the future, okay?
Absolutely.
Take care.